Thank you very much for joining us today. Let me acknowledge the traditional owners of the land, the Wurundjeri people of the Kulin Nation, and the elders past and present. It's great to have those who recently make Washington Post headlines and Guardian headlines, etc., about new synthesis of sea level rise projections. Sea level rise has been one of the major issues in the IPCC fourth assessment report. The fifth assessment report is one of the key impacts of climate change. Why do we care about 1.5 or 2 degrees? The countries at the Bonn negotiations just came together with a rather lackluster, lukewarm progress. But this is really, sea level rise is really at the heart of why we're looking so intensely into the mitigation option. Luckily, there are lots of co-benefits as well of mitigation, but if we need any reminder about why our journey to zero emissions is key, it's the coastlines on which we played it as kids, or the coastlines that we didn't play at, but where millions of people are having their residence and their livelihoods in the deltas of Bangladesh and elsewhere. So with that, it's my great pleasure to introduce Alexander Nauels. He had that as his research topic over the last 3 years. And let me also acknowledge the able guidance of David Caroli and Kathy McGuinness. Kathy, where are you? So here, Kathy and David being the co-supervisors.
And Peter.
And Peter Rader here. Being the co-supervisors of Alex. And it was a long journey. He built a new module in MAGICC. So there was a lot of sweat. There was but now luckily big success at the end. So with that, I would like to pass on to Alex. Questions for the end. It's around 30 to 40 minutes. And good luck.
Thank you, Malte. Thank you for that kind introduction. You've already acknowledged all the people that I wanted to acknowledge too. But so I can jump straight into pretty much, well, you actually forgot Matthias. He was now, unfortunately, he can't be with us, but he's in Berlin. That's the reason why he's not here. But yeah, thanks to my fantastic advisory panel and supervisor board. And I'm really actually quite excited to be in that situation now when I can wrap up and tell you a little bit about what I've done in the last 4 years, or at least tried to do in the last 4 years. So without further ado, I will take you on a little journey on sea level rise projections. Usually it's a pretty good starting point if you want to look into the future, to also look into actually what we know from the past, or even what we can observe in the present. So that's what I will try to do in a first step. If being this is very sophisticated. So okay, so you can see, what you can actually see here is the Antarctic continent, and this continent, this icy continent, has been in the news pretty regularly recently, simply because we've seen a lot of ice mass loss that hasn't been really accounted for 10 years ago or so. Even people thought that that continent would be rather stable because it was so cold. Unfortunately, what we know now is that help. No. Yes. So what we know now is that it actually loses mass, and quite substantially, which is worrying in a way, because Antarctica may potentially become a very key driver of future sea level rise. And you can see the regions actually on the right which lose the most mass, in particular the West Antarctic ice shelf region, West Antarctic region here. That's one of the reasons that actually worry us at the moment the most, because I think in 2014 already, or 2015, there were studies that suggested that this retreat could already be reversible. So no matter what we do in the future, this ice may go entirely, potentially contributing meters of sea level rise in the next centuries. However, from observations to projections to something like this, even a regional map which shows us New York City in this case, with a 2-meter sea level rise above the local high tide line, that's quite a long way to get there. And you can see in blue, you can see regularly flooded areas under this scenario. And what we basically have done in the last years, we've tried to elaborate on that path from what we know, how processes work, to future projections, because this is obviously not very straightforward to get to a number for a certain year, and then that's what we haven't done, but also to get obviously to regional or local signal. Let me quickly walk you through what the presentation will probably look like, hopefully. I will quickly run you through some key concepts of sea level, then highlight why we actually ended up doing what we've done. I will quickly present the MAGICC sea level model itself, but then hopefully spend most of the time talking about some applications and key results that we've been able to produce. In particular, I want to highlight the first sea level rise outlook that we've been doing for the new scenario generation of the shared socioeconomic pathways. Then I would like to draw some attention on the one of the key strengths of that new MAGICC model, which is basically extending 21st century sea level rise projections until 2300, and then give a quick glimpse on why this model actually also does help us to understand a little bit more about the underlying uncertainties. And I would like to finish, Malte already raised that point in the introduction, I would like to finish on an outlook on what the Paris Agreement may actually mean for sea level rise. And then a discussion in the end with hopefully some very interesting questions that I may be able to answer. Okay, so key sea level drivers. So we have the volumetric component of sea level, which is the thermal expansion of the ocean if it takes up heat. We have the glaciers, which have been crucial in 20th century sea level rise, which lost mass around the world. We have, which is probably becoming the most important driver in the future, the Greenland and Antarctic ice sheet mass loss. And we also have changes to land water storage, which basically now the signal is dominated by the extraction of groundwater, which also positively contributes to sea level. This is, however, not, at least not so far, a directly climate-driven component. It may be useful to get some key numbers floating around again, because especially from paleoclimatic archives, we can sort of draw some very, very important information on how future sea level may evolve. What we know, in fact, from the latest IPCC assessment, that whenever we had temperatures that were about 2 degrees warmer than present, or pre-industrial, sorry, that's important, we were looking at about sea levels around the world that were roundabouts. It's hard to put like a direct number in, but round about 6 meters higher than present. So that indicates already how much sea level potential there is for certain warming in the long term. From observations, we know that over the 20th century, we've seen about 20 centimeters of sea level rise, and we've also seen a marked acceleration of sea level rise over the last decade. So it's happening faster and faster now. And if we have a look at what the latest IPCC from 2013 told us about sea level rise projections, they've communicated an upper likely range of about 1 meter in 2100 for high emission scenarios, basically business as usual scenarios. But then, and that's a key thing now for what we've done, it became much harder for them to pull in all the information that they needed to provide very robust multi-centennial projections. For 2300, they assessed upper numbers of about 4 meters for high emission scenarios. However, they already acknowledged that these numbers may be too low because the polar ice sheet contributions may be underestimated. So, and this in particular is where our project comes in, because we wanted to contribute some new findings to the community that would tackle these deficiencies, in fact, provide longer term sea level rise projections, and also hopefully be able to assess a little bit more the uncertainties associated with those. The IPCC, as I said, they had low confidence in their numbers that they provided post 2100, simply because the available simulations were sparse and the scenarios were scattered. So process-based approaches, which are the most complex ones that we have, they are not really able to deliver such long projections, and they're not really able to also deliver these projections with a high flexibility regards to the input scenarios, just simply because they are computationally too expensive and it takes too much time. There have been simpler approaches floating around, but they all had their deficiencies in one way or another. The semi-empirical models, they sort of extrapolated future behavior from observed changes, which may not be capturing the full story. And there's been also some expert elicitations or so for the future assessment of individual components, which is also not ideal. So what we tried to do with the new MAGICC Sealevel model was to emulate everything what we know from process-based models and calibrate simplified parameterizations, merge them all together and provide then a consistent and coherent picture into the future. This is basically the model that we've come up with. And you can see in the bottom here on the right, that's the famous MAGICC model that Malte has been developing, hosting, and applying for more than 10 years, I think, in a way. That's probably true. At some stage, it always had some sea level information also attached to it, but it wasn't up to date anymore, and it wasn't comprehensive enough. So basically what we've done, we've added this thing in the back where we've parameterized all the 5 most important components with their individual contributions. And that's a very nice thing, because MAGICC is based on an ocean model, ocean upwelling model with 50 layers of ocean. We could sort of directly link that component to our thermal expansion estimates, where we basically feed in ocean temperature and directly calculate thermal expansion from what MAGICC tells us. So this is the sketch of what actually I've been, like the major chunk of my PhD was this, actually getting from this to this. So that one slide change is about 2.5 years. and I'm really glad that we finally actually ended up with plots like this, which tell us, and I will quickly walk you through this, that the MAGICC Sealevel model provides robust projections in line with the latest IPCC AR5 for the 21st century. So we've got a robust tool for global estimates, and we've also been confident that we can extend those estimates up to 2300. So you can see up in the top left, we've got the infamous RCP 2.6 scenario, which basically is the scenario that would hopefully allow us to stay below 2 degrees of warming with a likely chance. Sea level estimates in 2100 are around about 50 centimeters, a little bit less. And then we've got the RCP 8.5 scenario, which is the worst case RCP. If that's the worst case, after all, we don't know, but the worst case RCP scenario. And we've got median estimates of about 80 centimeters for 2100. The darker shading gives us the 66% model range, or the likely range, and the lighter shading basically indicates the 90% model range. So this is what we got. You can see, well, the bars basically give us the okay. On the right, you see the IPCC bar, which is, the bars are 2081 to 2100 averages. You see the IPCC bar on the right, and you see that our model is pretty much, it's not exactly where the IPCC was, also because we have got slightly different representations of contributions, but we are in the same ballpark, which is rather encouraging. So from this, we were able to pull everything together, and that was, I think that was the crucial thing for my PhD, that I was finally this year, only in June, actually, finally able to publish the model description paper. So it took quite a long time. We were obviously already working on results and everything, but this was sort of the stumbling block for my project, that this got published and it's now in the community and people can use it. However, when we were in that process of publishing, and we already started to update one of the components, because recent knowledge indicates that Antarctica may actually behave a little bit differently. There's two additional processes, hydrofracture and ice cliff failure, that were identified, which could dramatically alter the Antarctic contribution in the future. And so we've built a new parameterization that would be able to capture this contribution, which was a little bit tricky because it involves non-linearities. So we plugged in a threshold temperature. If that threshold temperature is passed, you know, the nonlinear part of the whole contribution could be captured with a rapid contribution. We've calibrated that. That's basically what we've done for all the other contributions too. We've calibrated our simplified parameterization with the reference data, and this is how it looks like visually. So you have the thin lines, the thin dark lines, which are the ensemble projections by DeConto and Pollard. They go out to 2500 and up to 17.5 meters in 2500, which is only from Antarctica, which is a very large number, excuse me. And we can see our model, basically the output that our simplified parameterization produces is the lighter, more transparent, colorful lines. So we manage actually to capture the process-based, much more complex projections very well with our simplified approach. Before I now jump into the probably more interesting results with you, I just want to quickly highlight why the MAGICC tool is so neat to assess uncertainties. On the one hand, we've got the key for climate projections is the scenario uncertainty, and another major driver in particular for long-term climate projections is the model uncertainty. So because MAGICC is so flexible and calibrated to emulate more complex models in general, we have the capability to feed of highly diverse, really different scenarios into the model, and get corresponding climate forcing output. So in this part, this MAGICC basically incorporates uncertainties from the carbon cycle, from what we know about how differently the global climate models actually respond to changes in forcing, which is usually captured under this equilibrium climate sensitivity term. And we are able to incorporate a lot of the uncertainties in the climate system and from climate models, and provide a probabilistic set of climate forcing, which is in our case 600 member strong probabilistic ensemble. So we have, for every scenario that we have on the left, we have an output of 600 climate model runs, and those are then captured. This is basically the range that you see, you know, the 90%, 66% range, and this then got fed into my new Sealevel model, where we now captured all the individual components and their best guess uncertainties, basically based on what we know from more complex models. Okay, so this is why we actually have a consistent coverage of the uncertainties in the climate system, also with regards to scenarios when we want to look at sea level rise. That's why MAGICC is so powerful. The first results that I want to present to you is a sea level outlook for the 21st century, how sea level may look like under the new scenario set of the SSPs. It's rather unfortunate. I've heard that many times that many people have never heard of these scenarios before. These scenarios will basically inform the new IPCC assessment report in 2021. So they will be used by the more complex global climate models and Earth system models in the next couple of years. And we've been able to sort of, because we have a simpler approach to, we basically were a step ahead in a way, and it's easier for us to process these scenarios with our little tool. So the big advantage of those scenarios now is that you have socioeconomic assumptions again. The RCP scenarios didn't really have this, and now we've got socioeconomic storylines which are captured with 5 SSPs that would allow us to get a better idea how, basically how the world looks like, what assumptions are going into these new pathways for the 21st century. And the handy thing as well is that the SSPs now allow us to clearly differentiate a case where we don't have any climate mitigation efforts, dedicated climate policies, and we have different levels of climate mitigation action. So we can say, you know, what's the difference between doing nothing and doing something. And these mitigation levels are, like for the RCPs, are captured with 2100 radiated forcing levels. So again, what we've done, we've applied the MAGICC sea level model now with the new Antarctic discharge functionality that we've added. And this is basically now 2100 sea level rise under the full set of SSP pathways. And I just want to highlight a couple of things. So the baseline case on the left here, that's the case where we don't apply any extra climate mitigation efforts. And as you can see in the bottom, the SSP5 storyline is the one that assumes continued fossil fuel development and high energy demand. And this is sort of the highest case that we get under the SSP scenarios, and the individual likely range goes up to about 2 meters now. So if you remember, we had like the IPCC AR5 talking about 1 meter in a worst case scenario with the Antarctic discharge functionality, which has to be proven still. I mean, this is not cut in stone, but it's a risk, and with that risk we end up at about 2 meters. The different mitigation levels basically show us that they take over for 2100. So in the best case, 2.6, that's comparable to RCP 2.6. We are looking at sea level rise 21st century, again of about 50 centimeters. A big advantage, as I said, was to look into what the individual scenario assumptions are of the SSPs. And we have a total of 105 pathways. So all the dots and triangles and things you can see on these panels are basically the individual pathways. And we can nicely relate then individual assumptions that are underlying those pathways to 2100 sea level rise. So that's what we've tried to do. And I highlight just 2 quantities that I've selected. It's the 2050 cumulative CO2 emission levels. And what we can see is that if we want to reach the lowest projected estimates for sea level rise with base, we should stay below 850 gigatons of carbon in 2050. If we now look a little bit more into one of those things that are now particularly handy with the SSPs, the information that we get, so primary energy from coal should be less than 5% if we want to stay with these lower targets. That is quite a powerful message, and it's much easier to communicate now that we can show these kind of things. So this basically would mean that we have to get rid of coal by mid-century. And now that we have the MAGICC sea level model in two setups, with the IPCC AR5 consistent setup that was published, and then the extension, which includes the additional, potentially additional Antarctic discharge. We are also, and that was handy, we could compare how these different setups actually pan out. And there's sort of two messages, one good message, sort of good message, and one bad message. The good message, let's start with the good message, is that if we stick to our commitment to reduce or to limit warming to less than 2 degrees, we may end up with the lower estimates of about half a meter, even if we assume that there's these additional Antarctic processes, which that's encouraged. I mean, 50 centimeters still requires a lot of adaptation. It will be very challenging for low-lying coastal communities. However, this sort of prospect is much more encouraging than the one up here, which tells us if we switch on additional Antarctic contributions, we will look at 55% greater sea level rise in 2100, if that is true. So if we really end up with an Antarctic that is much more volatile, that would contribute much more to sea level rise than we thought, we, instead of sort of the 85 centimeters median with about a meter upper likely range, we would end up with 132 centimeters or 1.3 meters, and the upper range, that's almost 2 meters up there. So that's a high risk that should be kept in mind when talking about future sea levels. This whole analysis, much more comprehensively, got plugged into this little letter for ERL, and that actually just a couple of weeks ago that got published, and that was very handy actually for my PhD too. So, as you know, you remember the SSPs allowed us to assess sea level rise for the 21st century. However, sea level in particular is not comparable to global mean temperature changes, and it's really important because it's so slow and its respond to look further than the 21st century. So we have to extend our analysis until, or as long as we can, pretty much. And the model, we were confident that the MAGICC sea level model can provide robust projections until 2300. And this is quickly just an overview of what MAGICC does with regards to temperature changes. You can see again the four scenarios, and you can see the black wiggly lines. This is basically what the global climate, the GCMs, the CMIP5 models, the really complex climate models tell us. And as you can see also, hopefully, and that's the important thing, that MAGICC does quite well in capturing these temperature projections. So we end up basically with a cooling for the extensions. Malte developed those extensions until 2300 in 2011, I think. And we end up with very high temperatures in RCP, up to 10 degrees in the median in 2300. And the 2100 estimates actually for RCP 8.5, I think, around about 5 degrees of warming or something like this. So we know that MAGICC provides a consistent picture with regards to temperature, which gives us more confidence in also putting forward those sea level rise numbers. This is the IPCC AR5 consistent setup, which gives us, indicates that we will look at around about 1 meter of sea level rise under RCP 2.6 in 2300 in the median. And down here somewhere, it's 5 meters under RCP 8.5. You may wonder why I've chosen that weird y-axis and didn't blow up the y-axis more below. It's because I want to show you the same panels for the case where we switch on additional Antarctic contributions. And this picture is rather different, as you can see. So I'm going back and forth. The only thing that sort of stays the same again is the likely range for RCP 2.6. However, and that's important, the low probability, high risk outcomes for RCP 2.6 go up. They go up to already about 3 meters. And if we look at RCP 8.5, we end up from like the upper 90% range of our projections in 2300 are up to 10 meters high roundabouts. We go up to almost 25 meters. So this is really scary, to be blunt. However, it is still important to remember that this case where we account for additional Antarctic discharge is not yet settled. So this is one study that was able to do this so far for Antarctica, and we are now waiting for other studies to come up that would either be able to confirm those or to basically contest those findings. If we, and that's the only thing that I want to elaborate on, uncertainties, if you now just look at the 2300 slice, just look, if we just extract that and have a look basically at what our 600 member probabilistic ensemble does, we can see that it's not normally distributed. You could also see that from the plots before. We can basically see that the majority sits more to the left. So there's more upper range, the 50% above, they span a wider range of estimates. So we end up in the IPCC AR5 consistent case, we end up with median estimates of about 1 meter, as I said, for 2300, and we go up to about 3 meters or so. For RCP 8.5, as I said, we have a little bit, like, we're looking at around about 5 meters for 2300, and we like the upper range, these are probability density functions go up to 15 meters or so. Very low, very low probability, but still part of this ensemble for very high climate forcing. And now if we change that whole picture, again, this is sort of the comparison between the two setups. The x-axis is the same. So we can see that the median pretty much, the median pretty much stays roundabouts that ballpark of 1 meter. However, we're seeing the tails are getting much longer for this Antarctic case, and the whole distribution shifts dramatically to the right under the new setup. It basically even reaches, for very high sensitivities, it reaches the maximum that we've defined for Antarctica, which is the 17.5 meters. So this is why there's basically a hard cut and a pileup of distributions right there, because there's nothing to the right anymore. This is something that we've defined in our parameterization, because that was the maximum contribution that was defined by the reference study. So actually, I would like to close the results section with this little outlook on Paris, which is quite handy given the current timing, and also the ongoing discussions what can be done, and if we are on track or not. We're definitely not on track at the moment, so this may elaborate a little bit on this whole discussion. So what we've done so far, and all the high mitigation cases that I've presented, basically everything that has had this 2.6 floating around, that was the highest mitigation stuff that we've covered before, and that would give us a likely chance of staying below degrees. However, the Paris Agreement is not only this target, it's much more than that, and it's also the criterion to aim at 1.5, and the last bit is the most crucial bit, actually, to achieve a net zero greenhouse gas situation in the 21st century. It was much more convoluted in the text. There was some elaborate I think, negotiating going on, but essentially what it tells us, the sinks, the balance between removals, I can't actually cite the balance between sinks and sources, means that we have to achieve net zero greenhouse gas emissions in the 21st century, and that's a really ambitious goal. So, and to achieve that whole package of the Paris Agreement, there have been studies around that suggest that we actually have to go down to much more towards 2 watts per square meters, or even below. Because we have not, and we wanted to elaborate on the long-term implications of this Paris Agreement. For sea level rise, we decided to come up with a highly stylized set of emission pathways that would allow us to look at this in more detail. Matthias Mengel is the primary author of that study, and Yuri, has always been heavily involved in scenario generation, is also co-author on that study, and this is currently in the final stages. We hope that it will go through. Let's see what happens. However, I would really like to quickly walk you through what we've done. You can see on the x-axis, you can see the timeline until 2100, and on the y-axis you see CO2 emissions. So what you can see is we've come up with two cases: a net zero CO2 emissions case in the 21st century, which allows us to stabilize temperatures, and a net zero GHG emissions, greenhouse gas emissions case, which captures the full Paris Agreement criteria set. So PA is the Paris Agreement. And we've assumed that emissions would rise. This is a stylized scenario set. So emissions would rise as observed until a peak year. And after that peak year, emissions would be reduced with rates of 0.3, 0.5, or 0.7 gigatons a year. These rates are highly ambitious. However, they've also been used already in the latest IPCC Working Group 3 scenario database. So we're not just coming up with a random number, but we're taking information from what we know from people that do this for a living. So on the left, we have temperature stabilization. You can see nicely that the temperatures stabilize below 2 degrees on different levels, depending on peak year and reduction rates. And on the right, and this is already sort of highlighting what we may be facing, the reduction rates that are applied cause a drop, basically cooling throughout the end of the 21st, 22nd, and 23rd century. For these two cases, we were that's how temperature responds, and it shows that we stabilize or even reduce temperatures, and we can see that sea level rise is definitely not responding that quickly. So for the temperature stabilization, we are still looking at rising sea levels in 2300. There's no chance we can stabilize sea levels under the stabilization case. We may be able to come close to stabilization according to our model setup, which is highly simplified. You know, we have to have all these caveats in there, but still, it's sort of a good starting point for discussions. You can see that the slope is flatter, and that we actually end up with less risk, low probability, high risk numbers. So we can save about a meter if we look at and that's the 90% model ranges again, if we go with full Paris Agreement compliance. This sort of outlook, I think, underlines very well that there have to be stringent and early emission reductions to have any sort of impact on containing sea level rise for the next couple of centuries. If we, even under strong mitigation cases on the left, where we achieve the 2 degree target, but not much more, we would still look at rising seas in 2300, and this is obviously a very large risk and a big thing to deal with for vulnerable communities. So to sort of kick off the discussion, in the beginning, I showed you this map of New York City with a 2 meter sea level rise scenario, which now, if we assume that Antarctica is going to go, we would actually have almost within our likely range for 2100. So this is, but now you know as well that not temperature, but time plays a crucial role in that whole equation. And it doesn't stop in 2100. Sea level rise doesn't stop there. It would basically go up much further. And if we assume that Antarctica would go, we end up in 2300 with a scenario like this. That's 20 meters. That's the upper end likely bound for our projections. And this is how 20 meters of sea level rise would look like in New York City in 2300. This is, you know, it's really hard to, this is a very scary picture, obviously, but we still have a lot to do to hopefully actually go back and even make it maybe hopefully even less than that. But it's important to visualize that we are facing these kind of risks with sea level, and that future generations will have to cope with that no matter what. And I hope that I could show that we try to make an effort to elaborate on these longer timescales to provide different projections for a wide array of scenarios. And I'm convinced that we could show at least that the MAGICC sea level model works and that it is able to elaborate on these questions. We can also see that it looks like even under IPCC AR5 consistent setups that we've used, that the numbers, you remember the 5 meters median up to 10 meters in 2300 are much higher than the 4 meters that were initially captured in the last IPCC assessment. So we have, but the uncertainties are extremely large, and we have to better understand what's going on, in particular in the polar regions. Last but not least, John Church says that every time he's asked about sea level, so one of the most senior scientists we have in the community, he's based in Sydney at the moment, he says we always have to adapt. There's no chance we can avoid adaptation for sea level rise. It is absolutely, there's no way around this. We are facing already now a substantial sea level rise commitment. The question is only by how much we will have to adapt. And sort of as an outlook, last thing that I will tell you, for better assessing regional impacts and vulnerabilities, we obviously need regional projections. And this is a thing that could be, initially I thought when I started my PhD that I could implement regional projections in the MAGICC sea level model, no problems. As you can see, it took a lot of time to actually only get to a global signal that is trustworthy, hopefully. And but this is definitely a thing where MAGICC can play a very crucial role, because we can easily feed into that regional effort and provide global numbers and expand actually our toolbox to include also these regional signals and fingerprints. So this is something that hopefully can be done in the future, and that comes out of my project. So I think that's it. Yeah, thanks.
Thank you so much, Alex. Alex was with the IPCC Technical Support Unit in Bern before he joined us. He had a planned sea level rise, cracking that nut or contributing to that. It was incredibly open and contentious issue, still is in a way, but he made a really substantial contribution there in his PhD. And having seen in the IPCC Technical Support Unit in Bern the whole range of issues, he could have chosen anything, but he wanted to do sea level rise. He did it, and it's a fantastic accomplishment, Alex, what you there did. So another round of applause for you. The one thing where I, as a supervisor, clearly failed. Did you remember when he said there was a 2.5 year between the one slide with the methods and the result slide? And did you feel that slight frustration there in his tone? I tried every single day to show him that in an academic life, he has the best time of his life. He can spend 2.5 years on model development, where on a really good day, like later on, maybe if you get to play around with code for 1 hour a day, you feel, yes, that was a good day. So I tried to show him that he has the best time of his life. It didn't always work. That was my failure. He will see that in retrospect. Now, we applauded him already twice. The time for niceties is now over. This is a completion seminar. This is like barbecue. This is like grilling. So if you have in your mind not just a very nice a question for comprehension, etc., but have something that can really go to the core about the modeling features, etc., or you found something inconsistent, now is the time. That is your role now as an audience to grill our PhD students. The floor is open.
G'day. Fairly simple. You mentioned a 600-member ensemble.
Yes.
Why 600? Where did that come from?
That's a statistical process basically that was involved, and this procedure was tested for years for work that also was previously done by Malte. So you have a much larger ensemble basically that involves a Markov chain Monte Carlo method, and you have I don't know, 85,000 or something. I don't know what you came up initially, but then you basically extract representative members that would still give you the full range. And in our case, we ended up with 600 members. So we had to, it was a balance between comprehensiveness, full comprehensiveness, and efficiency for the modeling exercise. So that's why it's a robust ensemble member. It has been tested many times, fortunately, before I applied it as well. So it's a 600. That's why it's a 600 member. So, Kathy.
Thanks, Alex. Great seminar. So MAGICC in past IPCC assessments, not the last one, but earlier ones, yeah, was a fundamental model for developing sea level rise projections.
Yeah.
In the last assessment, the process changed somewhat. The process-based models were used. The other contributions were brought in, some Monte Carlo sampling to put it all together to develop sea level projections. Now that you've updated the MAGICC module to the CMIP5 models, this model could be used to integrate sort of more of the uncertainty and develop sea level projections. How much of a job would it be, given that it took a couple of years of your thesis to update to CMIP5, to go the next step to CMIP6? And what's your thoughts on how MAGICC could be used instead of, you know, the lead authors of the chapter developing sea level projections to doing the job for them? Can you comment on that?
Well, the latter definitely not. So I think it's incredibly important to have that component where you draw all the different lines of evidence that also come from other sources, other modeling sources and other sources of expertise. So we had, in the latest IPCC assessment, there was a big discussion about process-based modeling is definitely needed to really robustly. That was a big thing for John Church, to have robust numbers for sea level rise. However, there was this the opportunity, like the option to go with much simpler approaches, the semi-empirical approaches that were published in that time. But they obviously had some methodological issues, and I hope MAGICC doesn't have any methodological issues. However, it's still a simplification, and I think it's incredibly important to wait what the process-based models will tell us over the next couple of years before the next assessment comes out. The MAGICC model then is always ready to implement the new input from the process-based models, but it has first to be produced by them. So we are not first, we are sort of always second in a way, but then we can use the model in a much more flexible way to look at different scenarios and different input. And so I would say it will be, now that this machinery is working, and I hope to understand how it works, it should be much easier for me to update individual component with new reference data. So if we know, okay, there's this great study that has come out and it seems to be the new state-of-the-art method to assess this component, it wouldn't take too long for us to update that contribution, as we've done for Antarctica already, and capture that new response. And I think that's a key strength. And if MAGICC was deemed by much more senior and much more experienced coordinating lead authors to make that contribution for the next assessment, that would be obviously great. But it's always, I think MAGICC is always very close, but always in the second step after what comes with the more complex and physically motivated approaches.
Thank you.
Hello, look, I'm obviously not an expert in the area, but there's situations like active area of ice, or sea currents, or acidity. How do you factor those in, or don't you factor those in your modelling?
It is in a way easier to produce a global signal because you get rid of the regional specificities of how sea level evolves on those smaller scales. However, so I am not accounting for small scale processes in my modeling. I'm sort of emulating what process-based, more complex models tell me on a global scale. They account for those little things, but I am basically taking the global signal and throwing that into my model. However, generally, small scale processes are accounted for. There are regional. Do I have a slide? There are a lot of regional processes that are accounted for actually, and it's completely crucial to do that. Gravitational signals, fingerprints, when we have lifting, basically uplifting still due to glacial isostatic rebound or something, because the Earth, sometimes when it was glaciated before, the Earth rises in certain areas still, the land comes up basically and compensates the sea level rise signal. All those things are known and quantified and are accounted for when we go on a regional scale. However, for this project, I haven't done that because it simply wasn't needed. For getting towards a New York City sea level rise projections, you would definitely have to do that. And if you didn't do that, you would have a very bad projection that shouldn't be listened to by anyone if you didn't account for these little processes.
Yeah. A very neat trick at the end of the talk to talk about adaptation, because it immediately got me thinking about this classic look over there technique right at the end of the seminar. So a question on adaptation timescales. And you've got a range of different processes on which the sea level responds, and a range of different forcings, and some of the responses are nonlinear.
Mm-hmm.
I'd be really interested to see, from the viewpoint of how fast we have to adapt, what the work you've done tells us, not only about how much adaptation we're going to have to make in the end, but how quickly we'll have to respond. So when does sea level exceed some set of thresholds,
mm-hmm.
As a function of the individual processes? So what processes are responsible for the fast response versus the slower response, and how those thresholds change as a function of how hard we whack the system.
Yeah. That's a very, very important question, and I'm glad. I hope I can answer that to some extent, at least. I got recently asked by somebody wrote an email and asked me, so what are the numbers looking for 2050? Because that's much more tangible. That's much closer. We may relate more to this closer time frame, and we can already see that there isn't too much divergence on earlier timescales with regards to scenarios. So we know we are committed to some sea level. In this case, in 2050, it's about, I think it's 25 to 30 centimeters or something. So that's something that we will have to adapt to in any case, no matter what will happen, because this is sea level that we are sort of committed to no matter where we go in the future, because sea level is such a slow responding climate variable. However, after sort of the first half of the 21st century, the scenario uncertainty really kicks in, and it's really crucial where we go with our emission pathways and how much mitigation we agree to do. And I think not only that, but we also now know that, it seems like the more processes we include at the moment, the higher our model uncertainty gets. So the less sort of, the more we know, the less we know. And what does that mean for our approach to cover risk? So do we go with the highest plausible ranges that we are producing with our projections, or are we sticking to the median responses? So I think, sort of wrapping up, I think, you know, it's really important. It's in particular for sea level rise to remember that it's not a quick responding variable, and we will have to look beyond the 21st century to really understand what we will be facing with regards to adaptation. And I think there have been a couple of studies already that try to quantify monetarily what it would mean to globally adapt to 1 meter of sea level rise. It's a monumental task. So it's nothing, even sort of our best case guesses to make sure that livelihoods are preserved and that coastal areas are safeguarded, and that the Port Phillip Bay, the heads will be closed or something, you know, so that Port Phillip Bay won't be, you know, whatever people would come up with. These things require a monumental effort, adaptation effort. So I will hope that I will in the future also be able to continue to look into this adaptation question, Peter. That's very important, yes.
I can see 1, 2 more questions. 3. Given the possibility that the colleagues of Alex just try to ask nice questions to save time for him and to get finished, I'm just injecting here 1 question at this point. If you could go back to your decontour parameterization, where you have the threshold here, this one. So you have a specific threshold temperature above which a certain nonlinear process kicks in. Let's say in one ensemble member, that threshold temperature is 1.6 degrees. If you have now 2 emission scenarios, the one lands you at 1.61 degrees and the other one at 1.59 degrees. But after 10 years, they come back to the same emission trajectory and stay on that for the next hundreds of years. What will be the difference in response in your parameterization? And how likely is that to be a true reflection of reality or not?
That's a very technical question. I will take you on that journey. I will try to keep it interesting for everyone else too. So it's really interesting actually, because as I said, we apply a simplified parameterization to capture those responses. Basically, we've assumed a more or less quadratic response for the linear part, and then once this ominous threshold is passed, we add a basically constant rate to whatever warming we see, so we can capture. You know, you can see there's no way you can capture this this range from. On the bottom we've got RCP 2.6, which goes up to 3 meters or so, yeah, and then we have got almost 18 meters or so for 8.5, and something in between that doesn't really allow us to go the linear way. So we had to find a tool to capture these non-linearities in the response, and that's what Malte is talking about, this threshold temperature. So we calibrated all the 3 parameters, and we got 1 threshold temperature per model member. So the Contour and Pollard, they used 20 or so models for the predictions. So we got 20 or so threshold temperatures for each and every model calibration. And in fact, we didn't get the same one for everyone, and that would be too easy. We actually ended up with a plausible range of between 1.9 to 3 degrees or so for kicking off this additional contribution. So, but as Malte says, once this kicks off, it kicks off. And in our case, if we go below the temperature again, it stops. So we'll, you know, and this, I mean, this is one of the, it's a little bit less dangerous because we're looking at anomalies, but generally this is a good indication that simplifications of the real world have, we have to make sure that we're very careful in how we communicate those caveats, because if we are facing an irreversible situation in Antarctica, as I've shown you in the beginning, where Western Antarctica basically goes, no matter what happens, it doesn't matter if we go back below this threshold or not, we would still see that additional contribution manifesting. So yes, that's my try, Malte.
The supervisors have later on a little bit of a round with Alex, so we can answer those questions then. In the interest of time, some of you might have to leave. Feel free to leave now because we are already 2 minutes over time. But I would collect the last 3 questions. So thank you very much for the participation for those who have to leave. I would collect the last 3 questions in a bundle, and then we have the last round. So if we go through here, Seb, and then Dimitri, and there was one question in the back. Is there another question? Yes.
Well, you've saved yourself some time, Malte, by stealing my question. So I'll just say well done and pass on to Dim.
Yeah, I was just interested in, you showed a graph where you have the mean of the IPCC sea level rise and your study, and the uncertainty range is far larger. And so for the ICP 2.6, you've got a much larger uncertainty range.
For the IPCC?
No, it's not this one. It's where you flick between your results and...
for 2300 or?
Probably
you say
2300.
This one? No. This one?
Yes, this one.
Yes.
Yeah. So for an RCP 2.6 scenario, your mean of the two is the same, and your uncertainty rate is much larger. So what are the processes that kick in to get you to these very high numbers, given that the temperature is staying sort of constant, 2300?
Yeah, Alex, thanks for that presentation. Really interesting. You mentioned, I came in a bit late, so I may have missed it, but you mentioned Antarctica all the time. What about the effect that the Arctic and Greenland melt will have?
Is that, can I now go? Is that all? Perfect. So I'll start with yours. Maybe that's okay. Absolutely true. The Greenland, in the beginning, I showed the video of Antarctica. We see accelerated mass loss also from Greenland. There is, however, and that's why my focus was on Antarctica. We haven't seen recently a study yet that would be able to quantify really these accelerations for the future. So we know that something's happening, and it's probably not good, but we do not know by how much. And since this approach only uses process-based projections, we have had no chance to really include those higher uncertainties also from that region. But you're absolutely, that's really important. And I should have mentioned that before. The polar ice sheet, I think the polar ice sheet discussion as a whole has to be looked at, not only Antarctica. There are different processes driving those. In Antarctica, it's more the ocean melt-induced contribution from discharge. In Greenland, it's more the surface processes where we have, because it's warmer, we have now much more surface melt that actually contributes to sea level rise. But yes, hopefully there will be studies soon that could allow us to also go and have a look at that.
So the projections then would be higher?
Probably.
Yeah.
And Dimitri, to answer your question, and that's sort of a building on what Malte asked me before. So we have used new reference data that actually has for RCP 2.6, the process-based projections that they've put forward span a range of even some negative ensemble members, and it's not entirely clear why, to up to 3 meters. So we sort of emulate this response range for the high mitigation RCP 2.6 scenario, and that's reflected in this bigger range. So whatever the process-based studies that we emulate and with our approach tell us, we basically reflect in our projections. So this is the full thing is the 90% model range IPCC consistent, and if we just only by including that new study, which has this enormous uncertainties with regards to how Antarctic sea level would respond, or Antarctic discharge would respond to this warming level, we end up with this new high range, and that's a testament to sort of to get a similar likely range. Basically, that's a nice way also of visualizing how important the tails and the low probability part of the distributions are, because for the 90, even though we sort of keep the 66% range, so the majority of the process-based members, they are in a similar ballpark. However, there are some that are much more higher, and this is what we get with that extended 90% range, and this is why, yeah, that's how this graph comes about.
Join me in thanking again Alexander Nauels. Thank you so much.
Oh, yeah.
We have some upcoming seminars now on Wednesday, the integration of demand-side response models in Australia from WIN. That is over in Earth Sciences, so don't come here, please. On Wednesday evening, there's also an Energy Future seminar organized by the Melbourne Energy Institute. That's in the Singapore Theatre. Next Monday at noon, we have Professor Jacqueline Peel here, Liability for Misleading Disclosure of Climate Change Risks. That should be a fascinating seminar. On the Wednesday thereafter, we have Nathan, our visitor. Nathan, are you here? Now, our visitor from Canada. The political test of the carbon curves, comparing 3 national climate policies, so Norway, Canada, and Australia, those countries who have large fossil fuel reserves, and how does it impact the climate policies. And then we have another fascinating confirmation seminar by Kennedy on the environmental governance through preferential trade agreements. So understanding those, look on our website, there are all the details. You can also join most of these seminars, at least those that are here via webinars from your home desk. Thank you again, Alex. Where did you disappear to? Okay, thank you so much, and see you soon.
Stuff.